All right, today we are starting section 1.2, which is titled Exploration with Patterns. And we need a fair bit of vocabulary, so like the whole front page almost here is vocabulary, just so that we can make sure that when you see questions and they use certain terms, you know what they're talking about, and that we're all on the same page with that, that language. So to start with, we're going to use the word conjecture. Conjecture is a statement or a conclusion that has not been proven. So usually when we say conjecture, it's something that we sort of think is true. Maybe even we have a really strong idea that it's true, but it hasn't been proven. Counterexample is something that proves a conjecture false. So if you guys say, my mom always gets mad at me when I don't do my dishes, and there's some random day when mom just puts your dishes away and doesn't get mad at you, that would be a counterexample. The one time, maybe the only time that she didn't. That's a counterexample. Inductive reasoning is a method of making generalizations based on observations or patterns. So when you wake up in the morning and you say, it was cold yesterday, and it was cold the day before, and it was cold the day before that, therefore, I think it's probably going to be cold today, you're using inductive reasoning. It's a pattern of what's been happening to figure out what's going to happen next. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So the way we're going to see deductive reasoning used is if you were, let's say, had an equation that said 5x or y equals 5x plus 2, and I gave you x, you could tell me for sure what y is. It's an equation that's given to you as a true statement. I give you one of the variables, you can give the other variable. That's kind of how we're going to see it used. Sequences are an ordered arrangement of numbers, figures, or objects. Sequences are first introduced in pre-K. So when the student sees triangle, square, what comes next? That's a sequence. Okay? We're going to focus our attention mostly on numerical sequences, right? And see those kinds of patterns. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, and a rule shows how to get the next term. So for example, if you see 1, 3, 5, 7, 9, and you recognized plus 2 is the next thing. I've got a pattern where I'm adding 2 every time. That's a recursive formula. What you would do is you'd notice the pattern is plus 2, and you could get the next term. Okay, that's recursive. A nth term or a general term is when you have a formula used to find that term of a sequence. So again, it looks like an equation. Somebody says to you the equation is 6n plus 3 when n is 7. What's the 7th term? Plug in 7, you get out the answer. You don't need to know the first 6 terms to know what the next one is. You just need to know the pattern by an equation. Okay, so you don't actually have to know the pattern by saying, oh, it's adding 6 every time. It's different. We're going to look at 3 basic types of sequences. The first one we're going to talk about is arithmetic. An arithmetic sequence, like the word arithmetic, right, is a sequence in which each successive term is obtained from the previous term by the addition of a fixed number. The reality is that it can be the addition of a negative number. It could be the addition of a positive number. It could be the addition of 0. It could be the addition of a fraction. There's no conditions upon what this fixed number or what that has to be, okay? So it could kind of look like it's almost subtraction, right? Because subtraction is addition of negative numbers. Are you with me? So sometimes arithmetic sequences don't look like they're adding, they kind of look like they're subtracting. That fixed number that's added each time is called the common difference. It's how one term changes from the others. Second type of sequence, geometric. This doesn't mean like geometry in the sense of pictures, by the way. But a geometric sequence is a sequence where the successive term is obtained from the previous by the multiplication of a fixed number. Again, you can multiply by positives, you can multiply by negatives. You can also multiply by fractions. So if you think about multiplying by the number 1/2, multiplying by 1/2 is the same as dividing by 2. So sometimes geometric sequences look like we're dividing terms because we're really multiplying by a fraction. The number we multiply by is called the fixed number, is the common ratio. Okay, it's a common ratio of a geometric sequence. All right, last type of sequence. We won't spend too much time here, but it's called a Fibonacci sequence in particular. The Fibonacci sequence is neither arithmetic nor geometric, but it's very commonly found in nature. Rings of trees, counting on the shells. You've probably seen pictures in classrooms you've been in before about Fibonacci sequences. So if you've seen it before, I know that you will be like, oh yeah, I remember what happens. But if you haven't, let me show you how the Fibonacci sequence goes. This is the beginning of the Fibonacci sequence. It continues. I'm not going to tell you have to answer the question per se, but has anybody seen this sequence before? I just want to know if you've seen it. You don't have to tell me about the pattern. Yes, a few of you have. I see some head nods. Does anybody remember what the pattern is to get the next term? Do you remember? What do you remember? Yeah, good job. If you add these two together, you'll get the next term. So we'll check it out. Like 5 plus 8 is 13. Yeah. 3 plus 5 is 8. So that's actually the way Fibonacci sequences work. So if you wanted to know the next one, 13 plus 21 would be 34. And then we could continue. So that's actually the patterning of a Fibonacci sequence. There is addition, but it's not the addition of a fixed number, right? Like I talked about with the other one. All right. This feels like such a funny place to put this in, but we're going to need it in a minute. So that's why it's here. It's the definition of exponents. If n is a natural number, if you have a to the n, which is a multiplied together n times, if n is 0, as long as the base isn't 0, then a to the n is 1. In other words, a to the 0 is 1. Again, I know it looks like a weird place for this to show up because all of a sudden, completely something not what I'm talking about. We're going to see it here in a second used, okay? All right, so back to sequences. In particular, we're going to spend most of our time with two types of sequences today, arithmetic and geometric. So again, arithmetic means adding something, continuing to add it to get the next term, same number every time. And geometric means multiplying by something every time to get the next term. So we're going to look at a couple of different ways of thinking about this. This one has 3 parts to every question. We're going to list the next 3 terms, which means we have to figure out the pattern. We're going to identify if it's arithmetic, geometric, or neither. And we're going to find the nth or general term. That's usually the part where people get stuck, that last part, part 3. So take a look at part A. See if you can figure out what pattern is happening to get from one term to the next. What is it? Add 3. So every time I add 3 to get to the next term. So if that's the case, what are my next 3 terms? 13, 16, what? 19. Okay, so this is like part I of this problem, right? 13, 16, 19. Next three terms. Okay, the second thing it said to do is to identify, is it arithmetic, geometric, or neither? So what is this one? Yeah, it's arithmetic, because arithmetic is the addition to get there. That wasn't spelled right. Let me try one more time. There we go. So it's arithmetic. Okay, so part 3, we're going to have to develop how we do that. All right, so think with me for a moment. If you add something together, just start from scratch. Don't look at my numbers here at all. That's not what I meant. Just if I wanted to add 3 plus 3 plus 3 plus 3 plus 3 a whole bunch of times, what's an easier way of doing that? Not powers, but you're real close. 3 what? 3n. So when you say 3n, how are 3 and n connected? They're multiplied. Okay, so repeated addition. When you add something together a whole bunch of times, it's a lot easier to do that if you know multiplication, right? So if I wanted to add 3 together 10 times, it'd be easier to do 3 times 10. Everybody good so far? So an arithmetic sequence, adding something together lots of times, is really multiplication by the number that you're adding. So we're going to start this exactly like you suggested with 3n. Okay? Because that's what I'm doing. I'm adding a 3 a whole bunch of times. But the thing is, I'm not just adding a 3 to nothing. Right now, this is just, if I plug in the number 1 here, I'm not getting any of the terms in my sequence, right? If I put in the number 1, I get 3. 3 is not in my sequence. If I put in the number 2, I get 6. 6 is not in my sequence. Do you understand that? Okay. So it is adding by 3, but it doesn't start at 0. It started at 1, right? But what I really need is I really need to be able to plug the number 1 in to this and get the first term. So I need to either add or subtract something at the end here that gives me the first term when I plug it in. So here's what I mean. 3n plus something here. I didn't mean n, sorry. When I plug in the number 1, I need to add something together to give me the first term, which in this one happens to be the number 1, right? What would I have to put in that blank spot to make that work? What is it? A -2. So if I put in the number 1, I'd get 3, and I don't want 3. I want 2 less than that. And you can check to make sure that it works by plugging in a few numbers. If I plug in n equal to 1, I get 3 times 1 minus 2, and that's 1, and that's what I wanted. What if I plug in n equal to 2? What do I get? 4. Is that what it's supposed to be? Yeah. So you can check to make sure that the number that you add or subtract at the end is correct by plugging in a couple of values to confirm. And it always works that way. If it's arithmetic, it will be the common difference, 3 times n, and then whatever you need to add or subtract to get the right first term. All right. How about the second one? How do I get from term to term here? So this one's multiplication by 2. Everybody good with that? Can we find the next 3 terms then? Okay, so what's going to come after 24? 48. All right, so this is part 1. I don't really quite have enough space on this slide. I should probably change that out at some point, but you know. Okay, is that good for the first part? Okay, second part, arithmetic or geometric? Yep, geometric because I'm multiplying, right? Cool. All right, so the part 3 is the tricky part. But again, once we do it one time, it's always going to work like this. Okay, repeated addition is multiplication. But what is repeated multiplication? Because that's what this is. I'm multiplying by 2 every single time. 2 times 2 times 2 times 2. Yeah, that's the exponents like you thought of before, right? Yeah, it's exponents. If I multiply by 2 10 times, that's 2 to the 10th power. So how do I write that? Well, I write it like that. Just like I did 3 times n, I'm going to write 2 to the power of n. Almost. So kind of like I needed to make sure that I start at the right value, I'm going to show you how we start at the right value here. And it's actually easier than it is with addition. Instead of making this n, we make it n minus 1. Because what happens when I plug in 1 to that exponent that now says n minus 1? You get 0. And what's 2 to the 0? 1. So catch this. The first term, which ours was 3, is multiplied on the outside. So here's the deal. Whatever the first term is, it goes on the outside. The common ratio is raised to the power n minus 1. The reason it's n minus 1 is because I want to be able to plug the number 1 in and make this equal, and make this whole thing equal to 1, so that it gives me the first term. On the outside is a 3. So if you want to think about maybe like an equation sort of perspective, this piece is the first term. This piece is the common ratio. And this piece is always n minus 1. And you can check to make sure it works. So just so that you know I'm not fibbing to you. I've kind of already mentally checked that this works for n equal to 1, but let's do it for real. 1 minus 1 is 0. And 2 to the 0 is 1. And 3 times 1 is 3. Let's try n equal to, just for fun, let's actually just jump to 3. N equal to 3. Okay, exponents first. What's 3 minus 1? 2. What's 2 squared? 4. And what's 4 times the 3 on the outside? I hope it's 12. Is it 12? Yeah? And that was our third term, right? So this is the right pattern. This is the general form. So this is part 3. Okay, question. Is this inductive or deductive reasoning? So flip back to the front of your first page there, where it discussed the difference between the two. Is this inductive or is it deductive? What do you think? Right. It's inductive. Inductive means I take patterns and I make a conjecture, an educated guess as to what comes next. And that's what we did. That's what we done, even just like the very first part 1 of this, right? I guessed as to what the next 3 terms were. I mean, it was like a good guess. It wasn't a random guess, right? But it was speculation a little bit on our part, that the pattern would continue in this way and these would be the next terms. That's inductive reasoning. Okay, let's try example 2. 2 parts on this one for each of my part A and part B, actually. It says using the nth term given. So on this one, we're starting with an nth term given. The last time we started with the pattern and we created the nth term. Now we're starting the nth term and we're going to create the pattern. We're going to find the first 5 terms of the sequence on part A, or part 1. Part 2, we're going to decide, is it arithmetic, geometric, or neither? Okay, only 2 parts on this one. So, we're going to find n equal to 1, n equal to 2, all the way down to n equal to 5. And the way we do that is we plug the numbers into 5n plus 6. So if I plug in 1, what do I get? 11. How about 2? 16. 3. 21. 4. 26. And I'll bet you can tell me the next one without even plugging it in. It'll be 31. And you can check, of course. And it is. What's the pattern? It's okay, Michaela. What do you think?
I don't know, like it's like 1, 1, 2, 2, 3, 3, 4, 4, and then it's like 1, 6, 1, 6.
Okay, you're right. But let's think of it in terms of addition or subtraction, multiplication or division. It's adding 5. Yeah. So the way that I get from term to term here is I add 5. Everybody see that? Okay. Now, that makes this a what type of a sequence? It's arithmetic, yeah. It's an arithmetic sequence. Can you look back at the equation, the nth term, and tell me why should it make sense that it's arithmetic? There's an addition sign, and there's something else too. And it's multiplication by the number 5. It's got the right pattern, right? Look back over here on the first part, part A. It's 3n minus 2, right? It's a constant times n, and then plus or minus something. So it's going to be arithmetic, and the reason it's plus 5 is because it's 5n. All good? Okay, let's try the next one. N equal to 1, 2, 3, 4, and 5. This one is n squared minus 1, so I have 1 squared minus 1. What is 1 squared minus 1? 0. I have 2 squared minus 1. 3. 3 squared minus 1. 8. 4 squared minus 1. Good. And 5 squared minus 1. 24. Okay. We're supposed to identify arithmetic, geometric, or neither. You're right. It's neither. Okay. You can rule geometric out immediately. Can somebody tell me why? I mean, like, immediately. Because why? There's a 0. Yeah, because there's a 0 in my sequence, it's 0, 3, 8, 15, 24. I can't multiply 0 by anything and get anything to 0, right? So that's done. There's definitely not going to be geometric. And if I try to do the addition, there's something very interesting happens, and we're going to explore this a little bit more here in a minute. This is plus 3, but what is this one then? Plus 5, and they don't match. But just for the moment, go ahead and find out for me what happens after that. Plus 7, and then plus 9. There is a pattern in the addition, right? There is, but it isn't the same number added every time. So let's finish this problem, and then I'm going to talk a little bit about the specific pattern that's showing up. Is this inductive or deductive reasoning? It's deductive. Deductive reasoning means that I start with a formula, a guaranteed rule, and then I make a conjecture based on that. All right? In this case, an equation. Okay, I want to take this sequence, this 0, 3, 8, 15, 24, and I'm going to flip to a different slide for a second and rewrite it in a different way. You can keep working there if you have the space for it, or simply find another space on your paper. What was after that? 15, 24. I just want to space them out a little bit more. Okay, so what we said is that this was plus 3, plus 5, plus 7, and plus 9, right? And we recognized that there's a pattern in the 3, 5, 7, 9. You might look at that and say, oh, look, they're adding odd numbers, and that's true. Or you might look at it and say, oh, look, it just adds 2 more than the previous addition did. Also a true way of thinking about it. What I'd like for you to do is to do the 3, 5, 7, 9 and do it again. If I look at this again, what would I have to add to get from 3 to 5? 2. From 5 to 7? 2. And from 7 to 9? 2. So this row right here is called first differences. And if you do it a second time, what do you think it might be called? Hold on to your socks. What is it? Second differences, actually. Okay. Now, suppose for a moment that they still didn't match and you did it a third time and then they matched. What do you think that would be called? Third differences. And if you did it again, it would be called fourth differences. So even when a pattern doesn't have a common difference, if you repeat the process a second time, it might, or a third time. So if you're trying to make a conjecture, and you will have a couple of these on your homework, where you're trying to figure out what's the next term, but the first ones don't all match, do it a second time. And if the second ones don't all match, do it a third time. There will come a point, I think it takes until a third time on one of yours, maybe the fourth time, but it's not going to go any further than that, where eventually they match. Now, when they match, it doesn't mean that it's got a name. It doesn't. The first one's matching, or the first difference is matching, is arithmetic. Okay, that's the ones we already talked about. There's not a specific name for the second differences or the third differences matching. They do create generalized formulas, but they're above what we deal with in this class. So you might notice over here that this equation, right here, I didn't mean to draw a line through it. That's what I meant to do. That equation right there has x squared or n squared in it, and it was a second difference equation. That's actually like y. If this had an n cubed in it, it would take you to the third differences before they would match. If it had n to the fourth, it would take to the fourth. There's a pattern for that, but we're not going to go back the other direction. You're not going to start with this weird pattern and create n squared minus 1. We're not doing that, okay? But that is a pattern as well that can happen when they don't match on the first differences.